Okay, let's take a deep dive. Our mission today is to cut through the noise and really pull the essential insights from the source material you've shared on backtracking algorithms.
Right.
We want to understand what backtracking is, how it works, where it's used, and, why it's such a powerful tool in problem solving. The kind of understanding that really sticks with you.
Absolutely. So backtracking is fundamentally an approach. Well, it's a method for finding solutions by exploring possibilities.
Okay.
It's kind of like navigating a maze, you know?
Yeah.
You try a path,
Uh-huh.
and if it hits a dead end, you back up and try another way.
And that backing up, that trial and retreat, that's the core idea here, right? You try something, and if it doesn't quite work out,
Yeah.
you step back.
Precisely. You step back to where you were before you made that move. The trial is taking that step forward, making a choice, changing your current situation or state.
Advancing down a path.
Exactly. Advancing into a potential solution path.
Yep.
And the retreat, that's actively undoing that choice.
Actively undoing it.
Okay. Yeah, and this is crucial. You need to restore your state to exactly what it was before you made that trial step.
Why exactly?
So you can explore a different possibility from that same starting point, that junction.
Right, right. I think the power of this really hits home when you look at specific problems. Let's not just define it abstractly. Let's see it in action.
Good idea.
The source material mentions classic problems, like placing n queens on a chessboard so none can attack each other. That seems, well, pretty complicated at first glance.
It does, but it's actually a perfect illustration of backtracking. The end queens problem, yeah.
So how does backtracking help us crack something like that?
Okay, imagine you're trying to place, say, 8 queens on an 8x8 board. Your state is the current arrangement of queens you've already placed.
Okay, the board as it is right now. So placing the first queen, is that our first trial?
Exactly that. You pick a square for the first queen, maybe top left corner, whatever. That's your first choice, your first trial step. You update your state, place the queen there on your mental board or, in your data structure. Now, you move on to place the second queen.
Right.
You find an available square, maybe in the next column, and place it. That's another trial. State updated again. You keep going like this, column by column.
I'm guessing this is where the retreat comes in. What happens if I place queen number 3, let's say, and it immediately attacks one I've already put down?
Exactly. That's where you've hit a dead end for that specific sequence of choices.
Okay.
That particular path isn't going to lead to a valid solution where no queens attack each other.
Yeah.
So you have to retreat.
Meaning?
You remove the last queen, you place queen number 3 in your example. You undo that trial step.
Take her off the board.
Yep. Restore the state of the board to what it was just before you placed her. Then you look for the next possible square in that same column 3, to try placing her.
So if the first square I tried in column 3 didn't work, I remove her. And then I try the second square in column 3.
Right. And if that doesn't work, you remove her again, try the third square in column 3, and so on.
Okay, but what if I try all the squares in column 3 and none of them work for queen number 3, given where queens 1 and 2 are?
Good question. What do you think?
Well, I guess you have to go back even further. Retreat past placing queen 3 entirely. Maybe back to the decision about queen 2.
Precisely. You've exhausted all valid choices for queen 3 based on the positions of 1 and 2. So you retreat past queen 3, nothing more to try there. Then you retreat past queen 2 as well. You undo her placement.
Wow, okay.
Then, from that state, with only queen 1 place, you try placing queen 2 in the next available spot in her column. And then you start trying to place queen 3 all over again.
So it's like nested backing up.
It is. This nested trial and retreat is how you systematically, methodically explore every possible valid combination without getting lost.
That's the core mechanism. Then try, hit a wall, undo the last thing, try something else. If you run out of options at that level, undo that step 2. Keep retreating until you find a branch with new possibilities.
You got it. You'd advance into potential solutions. That's the trial. And when necessary, you meticulously reverse your steps to explore alternatives. That's the retreat.
Okay, but solving n queens just by trying every single combination like this sounds like it could take, well, practically forever for a big board.
It would, absolutely. Brute force is usually way too slow.
The source talks about something called pruning to make this faster. How does that fit in?
Pruning. Pruning is where backtracking gets really clever and efficient. It's where we apply the problem's constraints to become smart about which paths we don't even bother exploring.
Constraints, like the rules of the game.
Exactly. In N queens, the main constraint is that no 2 queens can attack each other. Not horizontally, not vertically, not diagonally.
Okay, so how do we use that rule to prune, to cut branches?
Think about it. As soon as you place a queen in a square, let's say queen number 2, you immediately know which other squares on the board are now under attack from her.
Right, you can mark off the row, column, diagonals.
Precisely.
Yeah.
So when you're about to try placing the next queen, queen number 3, and you're considering putting her in a particular square, you first check, is this square already under attack by queen 1 or queen 2?
Ah, and if it is?
If it is, placing queen 3 there will instantly violate the constraint. It's an invalid move right from the start.
So you don't even bother trying to place her there. You just skip that square entirely.
Exactly. You prune that choice. You cut off that potential path immediately.
Because it's guaranteed to fail.
Guaranteed. That square is a dead end for this step. You don't need to explore any configurations that would start by placing queen 3 in that invalid square. You simply skip it and move on to consider the next potential square for queen 3.
So pruning saves a ton of work.
A massive amount. This cutting off of entire branches of the search space, branches guaranteed to be invalid, is what makes backtracking feasible for many complex problems.
Okay, so trial and retreat is how you explore the possibilities step by step, back and forth. And pruning is how you avoid wasting time exploring paths that you know are doomed from the start, based on the rules, the constraints.
That's a great way to put it. Pruning uses the problem's constraints to make the search much, much more efficient. Without effective pruning, backtracking can be incredibly slow, like you said.
Well, with good pruning.
With good pruning, you dramatically reduce the amount of exploration needed.
It feels like there's a repeatable logic here, a pattern. The source material presents this idea of a universal framework for backtracking. How does our N-Queens process with trial, retreat, and pruning fit into that general structure?
It fits very well. Many backtracking problems, N-Queens included, can indeed be mapped onto a standard recursive function template. Let's imagine this function may be called solve current state.
Okay, and current state for N-Queens would be what? The board configuration?
Yeah, the board with the queens placed so far. Or sometimes maybe just a list of which column each queen is in for the rows placed so far.
Yeah.
That implicitly defines the state.
Got it.
Now, inside this solve function, the first thing you usually do is check is solution, current state.
Is this it? Have we solved it?
Pretty much. For N-Queens, this means checking. Have we successfully placed all N-Queens on the board without any of them attacking each other? If yes, great, you found a valid solution.
And then you record it somehow.
Exactly. You'd call something like record solution, current state, to save this successful board configuration.
Okay, that's the base case, essentially. Did we finish, and is it good?
Right. Now, if it's not a complete solution yet, maybe you've only placed 3 out of 8 queens, you need to try making a choice to advance the state.
Trying the next queen?
Yep. For N-Queens, the choices are the possible squares where you could place the next queen, say the queen in the next row or column you're considering. So you loop through each potential choice for this next step.
And this sounds like where the pruning check comes in.
It is.
Yeah.
Absolutely. Before you actually commit to placing the queen, you check is valid, current state, choice.
Is this move allowed?
Correct. This function checks if placing a queen in this specific square, choice, given the current state, where the other queens already are, would violate that non-attacking constraint.
And if is valid returns false?
If it's false, you just skip this square. You move on to the next potential square, the next choice in your loop. That's the pruning action right there.
Got it. And if it returns true, if the square is safe for now?
If it's true, then the choice is valid at this moment. This is your trial step. You call make choice, current state choice.
Put the queen on the board.
Place the queen in that square, update your board state, your current state.
And then you dive deeper, recursively.
Yes.
Yeah.
You then recursively call solve. Again, but this time passing in the updated current state. You're essentially saying, okay, now try to solve the rest of the problem from here. You're trying to place the next queen on this newly modified board.
And when that recursive call eventually finishes, whether it found a solution way down that path or it hit a dead end and explored everything it could,
that's when the retreat happens automatically as the recursion unwinds. But crucially, after that recursive call returns, you must call undo choice, current state choice.
Take the queen back off.
Yes. Remove the queen you just placed in the make choice step. You have to revert the board state, the current state, back to exactly what it was before you tried placing her there.
Why is that undo step so critical again?
Because the loop needs to continue. You need to try placing the same queen, say queen number 4, in the next potential square in our column, starting from the original state, with queens 1, 2, and 3 placed. If you didn't undo the choice, the board would still have queen 4 in the previous spot you tried, messing up all subsequent checks.
Wow. Okay. So the is solution check, the eyes valid check for pruning, the make choice for trial, and the undo choice for retreat. Those seem to be the core building
They
blocks.
really are.
You just need to define what those actions mean for any specific problem, like n queens or Sudoku or whatever.
Right.
And this general recursive framework handles the whole systematic exploration process, the trial, the retreat, exploring all the valid possibilities.
Precisely. That's the beauty of the framework, its universality. Whether it's n queens, solving a Sudoku puzzle, finding subsets of numbers that add up to a target, or navigating some complex configuration space, you're essentially just defining these key pieces.
What's the state? What are the valid choices from a state? How do I make a choice? How do I undo it? When have I won?
Exactly. And when is a path invalid for pruning? You define those functions, plug them into the framework, and the recursive structure does the heavy lifting of the trial, retreat, and exploring systematically.
The source also clarifies some key terms we've been throwing around. Let's quickly make sure we've got those locked in, maybe using n queens again.
Good idea. Yeah, the source table is helpful here. Let's run through them.
Okay, first, solution.
For n queens, a solution is a complete board configuration with all n queens placed such that none attack each other. It's the final valid answer.
Makes sense.
Yeah.
Next,
Constraint.
the constraint is the rule, or rules. In n queens, the big one is the non-attacking rule. No two queens in the same row, column, or diagonal.
Got it. State.
The state is the current situation, the partial solution you've built so far. So after placing, say, 3 queens, the board configuration at that moment is the current state.
Right. Trial.
Trial is making a specific choice in advancing the state, like deciding to place the 4th queen in square 4, 5, and actually
Yeah.
putting her there, updating the state.
Then retreat.
Retreat is reversing that last trial step. So taking the 4th queen off square 4, 5 and restoring the state to what it was just before you placed her. It happens when you hit a dead end or after exploring everything down that path.
And finally, prune. Pruning is using the constraint to avoid exploring a path before you even make the trial step. It's deciding not to even try placing the 4th queen in square 4, 6 because you check first and see it's already attacked by queen 2. You cut off that potential trial.
Okay, that really clarifies how those terms map onto the process.
Yeah, and it's worth remembering, like the source notes, that some of these terms, especially solution and state, are pretty broad concepts you'll see in other algorithm types too, like dynamic programming or greedy algorithms. They're not exclusive to backtracking.
Okay, that terminology is crystal clear now, especially with the n queens example grounding it. So we've seen how this trial and retreat pruned search works and how powerful it can be. What are the trade-offs, the pros and cons?
Well, the biggest advantage probably is its ability to find all possible solutions. If you let the backtracking run its full course, like for n queens where there might be multiple valid ways to place the queens, it can find every single one. And as we discussed, with effective pruning based on strong constraints, it can actually be reasonably efficient for certain problems that would otherwise seem impossible due to the sheer number of combinations.
Right. It beats naive brute force by a long shot if you can prune well, but there's a downside, a but.
Yes, the main limitation is time complexity. In the worst-case scenario, maybe the pruning isn't very effective, or the problem just inherently has a massive number of valid partial paths to check the number of possibilities the algorithm explores can still grow exponentially, or sometimes even factorially, with the size of the problem input.
So for large problems, it could still get very, very slow.
It absolutely can. And related to that, space complexity can also be a concern,
How so?
primarily because of the recursion. Each recursive call adds a layer to the call stack, and the depth of that stack can become quite large. Plus, you often need to store the current state at each level of recursion, which might take up significant memory, like keeping track of the board configuration.
Okay, so potentially slow, potentially memory hungry in the worst cases.
Yeah.
Despite those limitations, though, where does backtracking really shine? What are the typical kinds of problems where you'd actually reach for this tool?
The source material breaks them down into a few useful categories. First, you've got search problems.
Search problems, like
Okay.
just finding stuff.
Pretty much. These are problems where you just need to find any instance, or maybe all instances, that satisfy certain conditions. Things like finding all possible permutations, rearrangements of a set of items,
Okay.
or the subset sum problem that's a classic. Given a set of numbers, can you find a subset that adds up to exactly some target value? Backtracking can explore combinations of numbers to see if any work.
Right, just searching for a combination that fits.
Exactly. Second category, constraint satisfaction problems. This is where backtracking feels maybe most natural.
Like N queens and Sudoku.
Perfect examples. You have a set of rules or constraints, and you need to find a configuration, an assignment of values or positions that follows all of them. N queens fits perfectly. Solving a Sudoku grid, you have to pick numbers for the empty cells while satisfying the row, column, and 3x3 box constraints.
Yeah, definitely rule-based.
Graph coloring is another one. Assigning colors to nodes in a graph so that no two adjacent nodes share the same color. Again, it's all about satisfying the constraints.
Okay, makes sense. What's the third type?
Finally, the source mentions combinatorial optimization problems. Here, you're not just looking for a solution. You're looking for the best solution, according to some measure, while still respecting constraints.
Best, like maximum value or minimum distance.
Exactly. Finding the combination of items with the maximum total value you can fit into a knapsack without exceeding its weight limit. That's the 0-1 knapsack problem.
Okay.
Or finding the shortest possible route that visits a set of cities exactly once and returns to the start, the famous traveling salesman problem.
Right, finding the optimal tour.
Yes. Now, here's a really important nuance the source points out. While backtracking can technically be applied to these optimization problems, you can find all possible solutions and then pick the best one. It's often not the most efficient approach.
Ah, okay. Why not?
Because for many well-known optimization problems, there are other, more specialized algorithms that usually perform much better. For knapsack, dynamic programming is typically the way to go. For traveling salesmen, especially large instances, people use sophisticated heuristics, approximation algorithms, maybe things like genetic algorithms or ant colony optimization. Backtracking might just be too slow.
That's a crucial distinction then. Backtracking is fantastic for exploring possibilities systematically and checking constraints, especially if you need all solutions that fit the rules. But if the goal is purely to find the single best solution in an optimization context, other methods might be faster or more practical.
Precisely. It's about knowing the right tool for the specific job. But understanding backtracking gives you this fundamental approach to exploring complex search spaces, a strategy that really underlies many different problem-solving techniques.
So we've really covered a lot today. The core idea of trial and retreat, the absolutely vital role of pruning to make it practical, this universal framework that helps structure these kinds of problems.
Yeah, the solution is valid, make choice, undo choice structure.
Right. And we looked at the types of challenges where backtracking is typically applied, like search and constraint satisfaction, breaking down a problem like N queens, and seeing how those simple ideas, trying a step, undoing it if it fails, and smartly skipping dead ends with pruning it really does make these complex-seeming problems feel much more manageable.
It definitely provides a systematic lens, a way to view problems that involve exploring lots of combinations or configurations under specific rules. It gives you a starting point.
And, I think that systematic approach, the idea of really trying a path, but critically, understanding when it's not working, and then fully retreating from that path before trying another.
Undo step.
Yeah. And using constraints to prune to recognize dead ends early. How might that apply beyond just writing code? Maybe when you're tackling a big creative project or making a complex life decision.
That's an interesting thought.
You try one approach, see if it yields results or hits, insurmountable obstacles. And if it doesn't work, you can't just sort of half backtrack. You maybe have to fully reset, revert the state to realistically try the next distinct option.
Yeah, acknowledging the undo is necessary before trying the alternative.
And maybe recognizing constraints, things that tell you early on that a particular path is likely futile.
That's a fascinating connection to make. The core principles, structured exploration, managing your state, evaluating against constraints, knowing when to backtrack, they definitely seem to have echoes in many non-computational problem-solving domains.
So if you, the listener, are feeling inspired to really solidify this understanding, maybe pick one of those problems we mentioned. Perhaps try solving a Sudoku puzzle yourself, consciously thinking about the steps, or look up an N queens implementation online.
Yeah, definitely.
And see if you can spot where the code is doing the trial, the retreat, the pruning check, and how it fits into that universal framework we discussed.
It's a fantastic way to see these concepts really come alive and click into place.